Access control is a time division multiple access, and this time division multiple access is just like we are using a round robin algorithm. And here we are going to, as the name suggests, it is time division. That means we are going to divide the time frames into time slots, and all the hosts which are available, or you can say all the stations which are there who wants to communicate, we are going to give each slot to each station in a round robin manner. Okay, like for example, if these are the hosts, this is representing a host. Okay, this is second host, the third host, and this is the fourth host. Okay, so these hosts are connected to a network like this: host A, B, C, and D. If they want to communicate with each other, now if this is denoting the time, then we are going to break this time into different slots like this. For example, the first slot will be given to the host A, second slot will be given to the host B, third slot will be given to host C, D, and again host A, B, and so on. That means we are going to divide these slots into some times, or you can say into some slots of time. This is, for example, slot, and will allow a particular host to communicate with other host within that particular slot only. Okay, now there's a question for this: how much time should we give to each station, or how big this slot should be? The question is how big this slot should be. This slot should be. How big the slot should be. Okay, now for these purposes, you can understand that in worst case what can happen. In worst case, the station on one end wants to communicate with the station on another end. For example, here, if in worst case station A wants to communicate with the station D, then at least we should give this much time that station A should be able to send the data to the station D. Okay, so you can view it like this. This is the first station. Assume station A1. Then this is the second station, which is assume the station A2. This is the third station, assuming this is the station A3. Up to so on, there are some AN stations. There are N stations. Okay, this is representing AN, and this is the link, or you can say channel, which they have. Now, in worst case, what can happen? The station A wants to communicate with the station N, AN. So, first of all, station A will place some packets onto this medium. Then station A will send these packets to station N, and then station N should be able to receive it. Okay, so you can say in worst case scenario, in worst case scenario, in worst case scenario, a station from one end, a station from one end may wants to communicate, may want to send packets to a station on another end. So to a station on other end, on other end. Okay, so at least, so you can say at least the time which should be given, the time which we should give, which we should give to each slot, to each slot will be equal to, will be equal to the time which allows this station to send at least one packet to the last station, at least one packet to the last station, to the last station, at least one packet to the last station. Okay, so you can see how much time will it take for a station A1 to send a packet to the station AN. So that time can be given as here it will be transmission time of one packet, plus if the station A wants to send this data to the station, to transmit this data to this station, so that will be called as propagation time, or TT plus TP. Propagation times means the time taken to travel in the medium, and transmission time is the time taken to place the data packet into this communication media, right? Or you can say to transmit the data into this communication media. Therefore you can say the minimum time slot which we should give is transmission time plus this propagation time, or you can say TT plus TP. Okay, and here we are assuming that all the stations wants to send the data of same size, therefore the transmission time for all the packets will be same. Okay, so you can say assuming that the data packet transmitted by all the stations are of same size, and equal bandwidth is allocated, okay, that is called as the transmission time. Okay, now we know what is a minimum minimum time slot. Therefore, if I can divide the entire time like this is representing the entire time or time frame. So you can divide this entire time into multiple slots like this, and the size of each slot, for example from here to here, this size should be equal to TT plus TP. Again, this size should be at least equal to TT plus TP. Again, this size this time or this slot should be equal to TT plus TP. Okay, so for example what we can do is, in the above example I can give this slot to station A1, I can give this slot to station A2, I can give this slot to station A3, up to so on. I can give this slot to station N. Again, in the round robin manner, I will be giving this slot to station A1, A2, A3, up to so on station AN. Again A1, A2, up to so on station AN, and it will repeat, right? So you can say the size of every slot should be equal to TT plus TP, and where TP is the maximum propagation delay which you can get from this channel. Okay, now if I discuss about efficiency in this case, then efficiency, we already know efficiency is always useful time upon total time. Okay, so here you can see between this complete time slot, the only useful time is the time when that particular station is transmitting the data. Therefore it is TT plus TP. So the total time is TT plus TP, and the useful time is only TT. Okay, so you can devise a very simple question based on this. For example, if you can say if TT is 1 millisecond and TP is 1 millisecond, then what is the efficiency you can get? Okay, so assuming this question, we have this question, assuming that transmission time is 1 millisecond, propagation time is also 1 millisecond. Now if n stations, this is a previous year question, stations are connected with this configuration, and each station requires 2 kbps bandwidth, 2 kbps, kilobits per second bandwidth, then how many then how many maximum stations can be connected to this channel or network. Okay, so let us try to solve this. Here they are giving the transmission time is 1 millisecond and the propagation time is also 1 millisecond. Then first of all, let us find what is the efficiency we can get. So efficiency will be tt upon tt plus 2 into tp. Okay, so efficiency in this case which we will be getting is 1 upon 1 plus 1, which is equal to 1 upon 2, or you can say it is 50% efficiency. Okay, now if we have a 50% efficiency, okay, here giving there's one more data which is given, that is bandwidth. That bandwidth is 4 mbps. 4 mbps. Okay, so efficiency is 50%. Now we have to find what is the effective bandwidth. What is the effective bandwidth, or you can say throughput of the system. Effective bandwidth is always equal to efficiency into given bandwidth, and efficiency is 50%, so it is 1 by 2 into bandwidth which they have given is 4 megabits per second, so it is equal to 2 mbps. Now with this 2 megabits per second, we have a total of n stations which needs to be connected, and they have given that every station requires 2 kbps bandwidth. Then how many stations can we connect? So if we have to connect n station and every station require 2 kbps bandwidth, then in total they require 2n kbps bandwidth, and this 2n kbps bandwidth should be equal to this 2 megabits per second, because it is the effective bandwidth. Okay, as I told you, because see, again I am telling you, when I'm measuring bandwidth, then my bandwidth is generally measured in the powers of 10, and when I'm measuring data is measured in the powers of 2. Okay, so there's 2 kbps, that means 2 into 10 raised to power 3 bits per second. Here 2 mbps, that means 2 into 10 raised to power 6 bits per second, so it is n multiplied by 2 into 10 raised to power 3 bits per second, and here it is 2 into 10 raised to power 6 bits per second. Okay, so here 2 and 2 are cancelled. 10 raised to power 6 divided by 10 raised to power 3, so it is n is equal to 10 raised to power 3. Okay, so how you can get 10 raised to power 3? So it is n is equal to 10 raised to power 6 bits per second divided by 10 raised to power 3 bits per second, and this bits per second is cancelled by bits per second, and this power will become 10 raised to power 6 minus 3, so it is 10 raised to power 3 stations. Therefore you can connect 1000 stations for the above configuration. Okay, now in the time division multiple access, in case of TDMA, this what we have to find, what are the disadvantages of TDMA. Time division multiple access. Okay, the first disadvantage is unnecessary waiting. Okay, so you can say what can happen is, if one station is not interested in sending the data, still we are reserving some time slot for that particular station. For example, if I am saying the station A does not want to send the data, and still we are giving him some time slot. So you can say in TDMA we are reserving a time slot for a station, and the station might not be interested in sending the data. The station might not be interested in using it. Okay, and still we are reserving a slot for him. Okay, then in that case whatever slot is allocated to the station is wasted is going to be wasted. So this is the biggest disadvantage of time division multiplexes. Now to remove this advantage, we introduced one more concept in case of time division multiplexes, and that concept is called as polling. Polling means before giving a time quantum to any station, we will ask all the stations that who wants to send the data. If some station asks for the time quantum, or you can say time slot, then we are going to give the time to that station, right? For example, if we have these are the stations, this station A, station B, station C, and this is the station D. We have these 4 stations, and these 4 stations are connected like this. Okay, so if this is representing the time, now we are going to divide the times in something like this. Like first of all, we are going to use some time for polling. Okay, you can say it is a time for polling, and after taking the time for polling, then we'll see in case of polling, these will, it is like a voting system. Like all these stations will vote that I want to get the time slot. If for example station A voted that I want to get the time slot, then we'll give the time slot to the station A, and this is T poll, is the time taken for the polling. So first of all, we are going to do the polling. Now if station A wants to send the data, then I'm going to give this much time slot to the station A. Then as soon as the time slot is finished, I'm again going to poll, and this time if I'm saying that station B wants to send the data, then I'm going to give the time slot to the station B, right? In the same way, this complete time will be divided into slots like this, where one slot will be for polling, slot will be for polling, where and another slot will be for transmitting the data. Again one slot will be for polling, then another slot will be for transmitting the data. One slot will be for polling, then again another slot will be there for the transmission of data. Okay, now here there's a benefit of this. The main advantage of this is that we are not going to waste any slot. We are not going to waste any slot. Okay, but the biggest disadvantage of this is we are wasting a lot of time in polling, right? So you can say we are wasting some time in polling. Okay, and secondly, there could be a chance of starvation. There could be a chance of starvation. Starvation means that if for example sometimes it may happen that station A and some other station wants to send the data, but every time station A is not winning the poll, right? So station A is not getting the time slot, it is not winning the poll, so we'll give the time slot to some other station. Okay, so it could happen that the station A might go to starvation. So here what is the efficiency we can get? Efficiency is useful time upon total time. Okay, so here in every case, what is the useful time? Useful time is only the transmission time. And what is the total time? Every time we have to do polling, then polling we have to do transmission plus propagation. So in total we have this efficiency is TT upon T poll plus TT plus 2 into TT plus TP. Okay, and again the effective bandwidth is always same, that is the efficiency multiplied by bandwidth. Okay, now the next algorithm based on this is CSMA CD. Okay, so let us look at what is CSMA CD.